This is the next video in the chapter on stoichiometry of chemical reactions. We have learned about limiting reactants and how to calculate how much product is produced from a limiting reactant and how much of the excess reactant is left over. So now we're going to talk about total yield and do a nice big example problem. So we need to move on to talk about yield, which is how much product we actually made in a process. This is a very important way of measuring how environmentally friendly and expensive our overall synthesis is going to be. So we did an example in the last video where we had 322 bread slices and 275 cheese slices. And we calculated the amount of product we could make from that. We determined that bread was our limiting reagent. And we determined we could make a maximum of 161 sandwiches from those raw materials. So we can make 161 sandwiches if the stars aligned and everything went perfectly. And so we call 161 sandwiches our theoretical yield. So a theoretical yield is the maximum amount of product that we could make if conditions were ideal. So every individual molecule of reactant turned into a molecule of product. We didn't make anything else in a side reaction by accident, and we didn't drop any of it on the floor. But we know that things happen. Some of those things are within our control, and some of those things are outside of our control, like side reactions happening in your flask. So if I was making that grilled cheese sandwich, it's possible that I might have burned a couple of them because I was making 161 after all. I might have gone to the bathroom and come back and burned it so badly that no one would eat it. Perhaps I dropped it on the floor and I couldn't remember the last time I swept the floor and decided it was too risky to eat. Or it's possible that they got snacked on by my family members before they were able to make it to the table. So my yield isn't going to be 100%. So let's say in my sandwich problem, we were only able to make 158 sandwiches due to a few sandwich casualties. So the number of sandwiches that I was actually able to make is called the actual yield, which is equally important because we need to know how well the process works in real life because we usually operate in real life situations. This is the actual amount of product made under real life conditions. And both of these values are important. It's important to know how much we could make if everything was perfect and how much we could make in real life. And so we want to report a number that reflects both of those. So we are going to report what's called the percent yield. And you may have done this before. The percent yield is a ratio of the actual yield, the amount you were actually able to make, to the theoretical yield, the maximum possible. And it's a percent, so we multiply it by 100. We'll box that. That's a formula we'll need to use in the future. Almost every time you do a synthesis in the laboratory, you need to report the percent yield to indicate how efficient your process was. So in my sandwich world, my percent yield was 158 sandwiches that I actually was able to make and serve over 161 possible sandwiches that I could have made if everything went great, multiplied by 100%, and that would give me 98.1% yield. Which, considering how unpredictable life can be in my kitchen, is a pretty damn good yield. So now that we know how to use stoichiometric ratios, how to predict limiting reagent and excess reagent, and how to discuss yield at the end of a process, we need to do an example in the chemistry world. So I'm going to give you a process to help you remember all the steps in solving the problem, and then we'll do a big example. So when I'm doing a problem like this, I follow a process. The first thing I do in my process is I balance the equation. Sometimes the equation will be balanced for you, and sometimes it won't. But you always want to check, especially if you notice that there are no coefficients in the problem. That should probably set off an alarm in your head. Make sure you check that it's balanced first, or else you'll use the stoichiometric coefficients and they'll be totally meaningless. So balance first, then identify your limiting reactant, because the limiting reactant is going to determine how much product you can make. To determine the limiting reactant, and then use it to calculate your theoretical yield. If everything went awesome, how much product could you actually make from that limiting item? Then we want to identify our actual yield. If you're doing a problem on paper, this is going to be given to you most of the time. If you are in the laboratory yourself, this is going to be a number that you need to remember to measure at the end of the lab. And when we know the actual yield and the theoretical yield, we can calculate the percent yield. And that's the number that we can report in the literature and in our lab reports. All right, so let's use that process to do a chemistry problem. Well, I have pre-written it for you, so go ahead and take a second and write that down, and then we will solve the problem. So this says when 277 grams of carbon tetrachloride is reacted with 115 grams of hydrogen fluoride, 187 grams of difluoromethane is obtained. What is the percent yield for difluoromethane? So here's the reaction written for us. So the very first step in our problem-solving process is to make sure the reaction is balanced. So we can check 1 carbon and 1 carbon, 4 chlorines and 2 plus 2, 4 chlorines, 2 hydrogens and 2 hydrogens, 2 fluorines and 2 fluorines. So the equation is balanced. So somebody has smiled upon us and done a little bit of the work. So our next step is to identify the limiting reactant. And it's a little bit too difficult for us to tell just by inspection. So the easiest thing to do is to pick the product that we already need to find in our third step and to calculate the yield, assuming that each of them is limiting, and then determine which one is the limiting reagent after all. So just like we did with the sandwiches, we will start with the first reactant, carbon tetrachloride. We need to convert this from the mass of carbon tetrachloride to the mass of the product that we made. So if we remember our table or our flow chart, we need to start with the mass of the first thing, convert to moles of the first thing, use the stoichiometric ratio to convert to moles of the second thing, and then convert back to mass. So we're going to have 1, 2, 3 steps in our dimensional analysis. So the first step is going from mass of thing A to moles of thing A. So we're going to use the molar mass, carbon tetrachloride, which I will calculate later. And we're going to convert from moles of one thing to moles of another. I want to start with moles of carbon tetrachloride, and I want to convert to moles of the product I'm interested in, difluoromethane. And my numbers for this conversion factor will come from the balanced reaction. So in front of the product, we have a coefficient of 1, and in front of the carbon tetrachloride, we also have a coefficient of 1. So that cancels. That was our middle step. And then for our post step, we're going to go from moles of product to grams of product. That's secretly the fastest way to solve the problem, because we know we're going to need to end up with the mass of the product anyway, so we might as well find it while we're calculating the limiting reagent. So moles of this cancels with moles of this, and I need the molar mass here. Okay, so there's 2 molar masses I need to find. I can calculate the mass of carbon tetrachloride as 153.8227 grams per mole, and the mass of this product as 120.914 grams per mole. So if we plug in 277 over 153.8 times 120.9, I got 218 grams of dichlorodifluoromethane is produced. That's when all of the carbon tetrachloride is used up. So we don't know if this is our yield yet. If this is our theoretical yield yet, we need to figure out how much we would make from the other product. So our other reactant is HF, dangerous stuff. Do not try this at home. And we're going to go through the same steps. We're going to go from grams to moles of that compound, from moles to moles into another compound, and from moles to grams of the second one. Whoops, that should be our circle. Some number of grams of HF per 1 mole of HF. And we'll go moles to moles. Moles of HF to moles of trichlorodifluoromethane. And we'll get our coefficients from the balanced reaction. So that's a 1 in front of the dichlorodifluoromethane and a 2 in front of the HF. And then we need to go from moles of product to grams of product using the molar mass of this one. There we go. Okay, so here's our very important middle step. Stoichiometric ratio. And then I skipped my molar mass calculation, so I've got to go back and do that. Hydrogen molar mass plus fluorine molar mass should be 19.149 grams per mole. And we did this one already up here. It was 120.914 grams per mole. Okay, so 115 over 19.1 over 2 times 120.9 gives us a yield of 363 grams of our product, if we were able to use up all of the HF. Okay, so right now we have 2 theoretical yields. If we used up all of the first reactant, we could make 218 grams of product. And if we used up all of the second reactant, we could make 363 grams of product. So we're going to pick the smaller number 1 as what really happens. So our 218 grams of product is going to be the correct theoretical yield. And that is because our carbon tetrachloride is going to be our limiting reactant, and our hydrogen fluoride is going to be excess. Again, this is something that we figured out at the end of the problem. I can't just look at the problem and tell you what the limiting reactant is for the most part. I have to figure out how much product is made, and the smaller one is going to be the limiting, and the larger one is going to be our excess. So now that we've identified the limiting reagent, we need to calculate the theoretical yield, and we've already done that along the way. So the next is to find our actual yield. Actual yield is usually given, so that one is given right here, 187 grams of product. That's our actual yield. The final step is to calculate the percent yield, which is going to be our actual yield over our theoretical yield times 100. Okay, so our actual was given 187 grams of dichlorodifluoromethane was made in this process. We know we could produce a maximum of 218 grams of the same product if everything went perfectly. Multiply by 100%, and if you plug that into your calculator, you should arrive at 85.8% yield, which for an industrial process is pretty darn good. So we start out with figuring out what is the limiting reagent and how much yield we could make from that limiting reagent. And then if we'd like to find percent yield, we combine the theoretical yield and the actual yield to find that percent yield. So now that we can do that successfully, we can check off the last components on our atoms first approach diagram. So we have just learned to do yield and limiting reagents, so we can check that off. And macroscopic properties we've talked a little bit about now, and we also talked about it at the very beginning of the course. So we can check that one off as well. Atoms first approach is complete.